Okay, we're starting, and we have 3 people in the classroom. We're going to have a lot of stuff to talk about today. Nothing that's going to be earth-shattering, but I have been working extremely hard to try to get everything done, which is pretty crazy, actually. So I delayed getting Project 2 finished until last night, and I still have to put a little bit of tweaking in it, and I haven't posted the updated notebook. But we'll talk about it today. Everything's in the project reader right now. It's just that I'm going to supply a lot of the code built in to a notebook. Right now it's in a notebook that is my solutions notebook, so what I have to do is transfer it to the sample notebook that you get from the website. So we'll start off with what I was doing the end of last week. As I was putting everything together, I decided I need to keep this link that you can see right here in the web page. I need to keep this thing updated if need be, but this is going to be your touch point for everything that's going to happen from here on out. And I don't know whether you think this is crazy or not, but there's no other way of doing this. I never actually thought it was going to happen like this. I thought Dr. Trimboli, when I agreed to this, was going to let me transition the course for the last few weeks to a totally different person that was going to be in charge. And I originally thought it would be Mark Frank. That was before I found that he had passed away. So I've got to try to manage all this, and it's going to be pretty tough when I come back, because I come back from my trip at 11:30 on May 4th in the evening through Atlanta, like we were talking about before class started, and then I have to be in here at 8 o'clock, so I don't know what the jet lag feeling is going to be like, but my due diligence is that I have to try to sleep a lot on the plane flying back home to try to get my clock working in mountain time again. But at any rate, if you go follow this link, this kind of summarizes where I'm at right now, and I may add a few words here and there, but I have set number 7 due on April 10th, and that's this Friday. An amazing number of people tried to turn that in last Friday, and I don't understand it, what's going on. I know people are paranoid about missing because there's been that problem, but I really want to talk about stuff today, and I'm going to give some hints. I've got to get my tablet out to you to talk about hints on the bonus problem. There are bonus problems scattered all the way throughout all the remaining problem sets, but this one will be due at midnight. But what I'm wanting on set number 8, which is already out there, and we'll be pressing into that material today for sure, that I want to be due at noon on that Friday. So that is a change. It's because I want to be able to post the solutions before I leave, and I leave early Saturday morning. So this class is just driving me like crazy. So I will talk about that again next week. It's due at noon, so that accommodates my posting. I may be able to do some postings of solutions and move them over while I'm gone. I'm not positive, but everything is accessible from my tablet that I'm taking with me. But that doesn't mean I'm dialoguing with you on Slack. I'm just going to have to, do pushing and checking problem sets in if I can. I'm not super anxious that I'm going to have access to everything, because the last trip I did with Viking a year ago at this time, the Wi-Fi was very spotty, and it just didn't really work all that well. And I have a sibling of mine and my wife and his wife, and they're all going to be looking at me like, what are you doing if you're touching any work stuff? But anyway, we have set 8 due, and then the big news is, not new news today, but I announced it already, is exam 2 will be taken on Tuesday the 21st. And I'm just settling from the general rumbling I was hearing last week after class in the lab that we will have the exam start at 9:15. Now, whether or not Chirant, who's the lab instructor, will want to come in here at 9 or earlier, but I won't be doing a lecture then. I may have a video for you to watch. I may have a video to watch for the following week because that's just kind of nebulous right now. I have the old videos, but I have to map them in, and I'm going to rely on them to some extent. But you know, they were made during COVID. They were made right when COVID started. The last few videos at the end of the semester, I was sitting at home. I was getting used to teaching at home, and students were getting used to watching. And all of you can remember that. It was not, the whole, everything kind of got better and better and better as time went on, but initially it was pretty cranky. I would lose my connection, and I'd be lecturing to myself, and I'd find out that I had dropped the video call that I had set up. My lecture was still there because I was recording that locally, so that will be okay, but there'll be strange things where people will message to me saying, you know, your video dropped. Does anybody remember experiences like that? There was just a lot of uncertainty. So it's not the greatest stuff. Time permitting, I'll try to sit down and do some new lectures. But then Project 1, I moved that out to the 24th. We're going to talk about it this morning. It's now pushed up there, except for the notebook. And I'm just really, everything that you see on this schedule is for your own good. I mean, I don't like letting things pile up, and I don't want you to use my gone to get further behind, because we're going to run out of time. Absolutely. No class meeting on Tuesday, April 28th. I hope to have the new video, like I say, but if not, you're going to watch a 2020 video. Set number 9 will be due Friday, May 1st. That's just before I'm returning. I'm just posting that as a nominal best thing because there's one more set that will be due the following week, and that's leading into finals week. So you can see Tuesday, May 5th, I'm back. We'll be reviewing for the final exam, and I'll have the final lecture, which is going to be laying heavily into Appendix A, which is very easy material. That's something that I'm just going to say right now. Appendix A material is very easy, straightforward. It's just good material to cover on noise figure, noise modeling, and communication systems. And Dr. Song used to do some of these things in, I guess, EMAG 2 maybe. Does anybody, have any of you remember going through noise figure calculations and noise modeling? Okay.
Yeah, I try not to.
Okay. It's not really hard. It really is, to me, it's the best in communication systems because we are the ones that use it the most. And the link budget is one of the very last homework problems in that area. It's pretty straightforward stuff, but I get to talk about isotropic radiators and things of that sort, and aperture area and antenna gain over isotropic, some of the things that you do in electromagnetics as well. So then set 2 will be due on May 8th, and then the final exam, I've looked that up. It's due, it occurs from 8 to 10 a.m. Sorry to say, that's the exam time that's been given to us. I can't change that, so you're going to have to get prepared to arrive at 8 a.m. on May 12th. And then, just to give a little bit of flex time, I'm saying I want Project 2 due no later than noon on May 13th. And in reality, I don't expect anybody except maybe 1 or 2 people that will do that. Most everybody will get it done, and they'll turn it in by the weekend or something. That's just been historically the way it works. But it's there as an option to have a little bit of time to take a break from it to make sure you can study well for the final. And the final project is, in part, already posted from back in 2020, but I'm going to tweak it, and then I'm going to add one little section to it. So just keep your eyes on this. This table is not going to get bigger or smaller. I just may update some things and write some more comments. And another thing I'm going to say for all of you that watch the video later and those that are in the class, if you see anything that doesn't look right, let me know on Slack as soon as possible, because I'm so pressed with so many different things I'm trying to get done that something not at all obvious to me might be in here, and you might see it and say, wait a minute, this doesn't make sense. So I want this to be really at the top of the game. I want this to be something you can say, I'm having problems figuring out when a due date is and so on. You can just look at this immediately and just see how it all rolls out. So now we're going to drop in and take a look at the project. And like I said, that is now been reposted as the reader. The sample notebook just has to I have to transfer stuff from my solutions notebook into the sample notebook that'll get posted. But we're going to take a look at this, and I guess I didn't open up the link yet on this computer today. So I changed the due date in here, and I changed the sentence at the end here. I said, turning in the project earlier will free you up to do other classwork. Just keep that in mind. What am I doing? I'm going crazy trying to do all this advanced work, but I'm doing it because I have no choice. I mean, I'm leaving, and I'm not going to be working on it while I'm traveling to any extent. So just, being a college student and teaching a college class are two things that are so intensely bound to the calendar. I mean, the work I'm doing for the company, I'm having 2 weekly status meetings in front of other people. I'll have one late this afternoon because they're so worried that they want to get as much of my brain dumped out before I leave. And they're just super worried too, but I don't consider it to be nearly as worrisome as the timeline that the teaching falls on, because it's not movable. So the second problem is what I'm going to take a look at. Some of you have said that you've gotten through problem number 1, and if you jump to the end of this, and this is what I still have to flesh out, I will be putting in the point values for each of the problems. And right now there's 8 tasks in problem 1, but they're pretty small little snippety things to do. In problem 2, there are only 3 tasks, and there's not too much to do in some because I've written all the code out. You just have to exercise it. A little bit more work in task 3. And I'm honestly thinking right now that if I can't clarify things within my short time window, I may remove task 3. I might just say omit it. And I've had to do this stuff before. It's like accepting failure to me. I take this stuff probably too seriously, but I take it pretty serious. So, okay, so what are we doing with PCM encoding and decoding? We demoed that in class. It's in the Chapter 3 Jupyter Notebook. And these two functions are just highlighted here again, the PCM encode and then PCM decode. They work back to back, and they're the means of taking the analog signal samples, converting them into a bit stream. So each sample, in this case, I've shown that the number of samples per bit is 8. So you have a serial bit stream that's composed of, as this picture shows over here, looks kind of like this top timing diagram where you see word sample 0, 1, and so on, up to, in this case, I've counted up to the number of frames, and it looks like I can see a typo error in here too, but it should be n frames, but I start at 0, so I've got one more than I need to. At any rate, and this is how the data is sent. PCM is used in telemetry to this very day, and it's actually pretty popular in spacecraft things. One of the things that spacecraft do is they have missions that they carry out, but another aspect of a satellite And any other devices that we use, like our cell phones and things, there's telemetry data in effect, especially on satellites though, that inform the status and health of the satellite and all the subsystems on it. So how are you going to get all that sensor data from the satellite back down to ground to monitor it? And sometimes it's only when it passes overhead that you can get it back and update it. So they use PCM for a lot of applications here. They're going to encode sensor data and other interface data into a serial bit stream, and then the bit stream gets decoded, and then you get the values for the housekeeping. And right now I'm thinking of the Artemis II spacecraft that's come around the backside of the moon last night. Not everything that the astronauts do is, they don't, read all the instrumentation and tell everybody on the ground. Now, a lot of it's handled with telemetry, so the telemetry is always operating, and you can multiplex together a bunch of PCM data, and that's what we do here. But one of the big showstopper things with a serial bit stream is frame synchronization, and that's what you're going to explore. Just play with it in task 1 of this problem 2. What you do is you insert a sync pattern, and it's called SP in this notation. And I decided to use SP because the system I'm working on, the LunaNet AFS, which is the GPS system for around the moon that I'm working on right now at my work, they refer to the frame synchronization pattern as SP, sync pattern. And we're actually using the sync pattern from that project because I have a link. I guess it's right. It comes up a little bit later, right down here. This link down here takes you right to the LunaNet standard, and you can see exactly where the 68-bit sync pattern is defined in that requirements document. So what do we do with frame synchronization? You embed into the serial bit stream a sync pattern, and then you set up so many PCM words, as I refer to them, 8-bit words in this example, and I just arbitrarily said let's have 500 PCM words of 8 bits contained in the so-called payload portion of the frame. And payload is just a convenient term because literally that's what it is, right? You're going to send some housekeeping and other information, and then you're going to have your payload, which is all the valuable stuff that you want to extract back. So we have a sync pattern included, and at the transmitter I have this function that I've written. It's defined in this document, but it will be sitting in the sample notebook as soon as I move it in there. It's called toSPPCM stream. So it takes the stream of PCM words coming out of the encoder, and then it wraps them up in this framing structure, repeating the sync pattern every, in this case, 500 words. And then at the receiver, we have to do 2 different things, and what I've supplied in the code base again is 2 other functions, one of them to find the sync index, so it finds the sync pattern and then tells you where to start marking time to put things back together again. And then finally, the second receiver function is one that takes and unpacks the sync pattern from the serial words so you can go into PCM decode directly. So this is sort of, it starts out up here saying we don't have any way of keeping track of where we're going to land. If there's a delay, or we don't know the exact epoch or epoch, however you want to pronounce that word, of when the bit stream arrives at us, we can find out where the word starts, and that's what the sync pattern is doing. So you can see I'm prepending the sync pattern onto the frame, and then in the specific example of 8 bits per word, this is what it would look like rolling along. So we have 4,000 total payload bits, and then we have 68 bits of sync pattern. So here are the functions. Like I said, you could cut and paste from here if you want to get started immediately. I will get to this later today. This is the sync pattern, and it's given in the standard that I pulled it from as a hexadecimal string. And then I converted it to get a binary string out of it, as shown here. So how do we actually locate a string, a known string? The most common way of doing it is using a cross correlation. And I like to think of it as cross correlation. A microcontroller digital systems person might say, oh, I'm going to, I don't know, and if you have a word for it, if you were looking for a pattern, what would you call it? I'm calling it a cross correlation because that's what we've already talked about in this class. But you could do something with a shift register and XOR outputs of a shift register, you know, as the data slides into it, and keep testing it to see, is the pattern here? Is it here? Is it here? You know, keep moving along. So that's one way of thinking of it. I think of it sort of from a systems level, top down. The first thing we have to do, though, is we map the 0, 1 bits to levels of plus and minus 1. The reason why we have to do that, when you're trying to correlate, you can't really correlate with a 0 amplitude level as well as you can if you give it a bipolar amplitude. So we convert it to bipolar, and that happens to be the way it gets transmitted anyway in most digital modulation schemes. So what we have to do is find, through cross-correlation, where the first occurrence of the sync pattern occurs, and then I find a second one, and then I know I've got it. So this is what the code does. The code will take a short, like 2 frames of data, 2 complete frames of data, and it will say, okay, I got my first correlation peak right here. It's not at the beginning because in this code I'm inserting a random delay just to model the effects of a real world scenario. So if we go up into here, you can see at the top of the function that inserts the sync pattern, I'm putting in a random time shift, and I prepend that down here with just some zeros just to say nothing's here and the waveform hasn't quite arrived yet. At any rate, so I find it once, and then I go a whole frame again in my capture buffer, and I see a second correlation peak, and I verify that I crossed a threshold. And what is the threshold? The maximum correlation I'm expecting if I've got a 68-bit pattern is what? Just thinking of a normalized correlator. If I see 68 bits with a correlator type structure, I should see 68 as a number, right, as an integer. Because I'm putting in plus and minus 1 values for those bit values, I will get other values out of the correlator. And what am I relying upon from probability theory? I'm assuming that 68 bits of this exact pattern are going to not occur with a high probability. And you can go through that analysis from probability theory, right? You can say a random 68-bit pattern out of random bits is going to be very unlikely. It's not 0, but it's unlikely. So a sync word detector is not infallible. Does that make sense? Just random occurrence, we might get a random hit. If we get it 2 times in a row, though, that's even less likely to happen at random. So this is just a rule of thumb to say we're going to see 2 of them before we declare that we know the alignment of the sync pattern within our bit stream. And the way I do this in the code is I give it a long enough record so that I should be seeing 2 peaks in here, and then I also check that the difference between the first peak and the second peak corresponds to the separation of the sync pattern. Is all this stuff making sense? This is not linear systems theory. This is more or less just digital logic and housekeeping. But you can see in this particular case, there's quite a bit of cross-correlation well below 68. So I set the threshold at 67. but it's adjustable. So you're going to play with this in task 1 of this problem. And I have a mode that you go through in this find sync. I have this optional parameter called cplot, which stands for correlation plot. Normally it's set equal to false, but if you set it equal to true, it generates this picture for you. So, and I'm asking you to do that in task 1. So now what is our top-level system block diagram of this complete digital comm system using PCM? It's showing right here, and I guess I talked about this probably already, but I've added more to it. We have an analog message source. We're now going to put our sync pattern framing in. We're going to put a PCM encoder. I can't believe this, but I've been pretty tired working on stuff. These 2 blocks are reversed. This should be in front. Analog message source gets PCM encoded, and then we add sync pattern framing. So that's why I'm going through this, because I need to find all the things I need to fix. This will get fixed, though. I do have it right down below, but I guess I can draw on this. Did anybody see that before I said anything? Okay, have to encode into bits first before we can add bits in. Then we send this over a channel. If we don't put in forward error correction coding, we'll just couple it directly to bypass the encoder, and then we send it through a simple waveform channel, which in this case is not very sophisticated. It's just a simple way of testing our system. We're going to level shift again to go between 0 and 1 bits to minus and plus 1 to model a 1 sample per serial bit to represent our radio channel. And we're going to put additive noise in there to corrupt it. And I ran this a couple weeks ago in the class. And then at the end of this channel, we're just going to make a hard decision on whether or not it was a 1, plus 1, or a minus 1. And then level shifted back to 0s and 1s. And then we're in the standard scheme for doing more digital bit type processing. If we decide to go with forward error correction coding, we'll be going through the Viterbi decoder. And this is used in part number 3, or task 3, where the forward error correction coding is introduced. After the bits come out of the decoder for the Viterbi algorithm processing convolutional codes, we then find the sync index and apply that to removing the sync pattern and getting the serial bit stream back. They can go directly into the PCM decoder, and then we can listen to it or process it. So the additive white Gaussian noise channel is just adding Gaussian random variates to the plus and minus 1s to represent noise that's in the analog domain. And we'll be talking about that in Appendix A, but just to give you a little preview of it, we have thermal electron agitation due to the fact that we're not at absolute 0. So we generate a small noise voltage across any analog electronic circuit. And communications waveforms are very susceptible to that, and you're saying, well, we'll just send more power, we'll never see that noise. But we don't want to send massive amounts of power because we want to make our signal travel a great distance. Again, I'll think of the Artemis 2 mission up there. It's coming all the way back to Earth, and they're trying to keep the power that they have to transmit with as low as possible so that the solar pack that's powering everything on the spacecraft can last a long time. So this just goes through the details. This function actually is already in digital comm. It'll just be in your code dc.awgn channel, and that'll be shown in the notebook as well. So when there's random noise added to the bits, then we have to go through we can go through a calculation of making a bit error. And what that reduces down to is saying what's the probability that the noise is large enough to flip the bit, to make it flip from a -1 to a +1 or vice versa. So the analysis for that is to say that it's this equation, which involves the complementary error function, also similarly related to the Q function, which is this integral number 4 for the tail of a Gaussian PDF. Now, I know that random variables is not a requirement for this class, but how many of you have never seen a Gaussian random variate before? Because you're now taking probability theory. Everybody's seen it, right? What do you do with random variables anyway? In life, I mean, as an engineer. I mean, I look at it as kind of two main things. For me, in common signal processing, it's a lifeblood thing because we have noise, we have errors. But in other areas of electronics, we use random variables and random variable modeling just to go after lifetime of components, lifetime of systems, failure analysis, of this, that, and the other thing. You can use it for traffic modeling. I'm looking at the street out there thinking of a traffic light. That's a flow in a bit pipe, in a sense. You probably never thought of it that way, but as you drive through Colorado Springs, you're getting clocked through the system at various gates, right? And those gates are triggered by the timers on the stop and go lights. And then the amount of traffic that fills up the pipe is like bits in a bit pipe. Congestion occurs just like in the internet, so you can statistically analyze throughput and latency that you have in a digital data communications network as driving. Has anybody ever thought of that? Unfortunately, because I've been doing this all my life as a working engineer, I think about it a lot, and I used to go skiing up in the mountains, like in Summit County, for example. And if you come back on I-70, how many of you have come back on I-70 on a busy day of skiing, let's say? What happens as you come through the tunnel and you start down from there, usually you can have seemingly waves where the traffic gets really slow, and then it will speed back up again, then it gets really slow. Has everybody experienced that? It happens on I-25 too, but have you ever thought, why is this happening? I mean, I don't have the exact answer, but I've always thought statistically I could model that in a network type simulation as packets and congestion. There's some phenomenon though that happens. It's almost like a standing wave pattern that you get on a transmission line where you have peaks and valleys, and that represents, you know, your changes in latency and propagation time through the network. It's a curiosity thing to me, and believe it or not, there's a whole branch of that in civil engineering, traffic modeling, and Colorado Springs practices that to some extent, but if you're a little bit like me, you'd say, I can't believe that they were actually optimizing this, but they do have lights. I mean, they do have cameras at all the intersections, and they can modify the timing on the lights depending upon whether it's inbound or outbound time of the day, and they can tweak it. Does that sound too far-fetched? I would just wish they could do better at it myself. And then there's what I call the random access intersections, which come from side streets in small neighborhoods where they can drive up to the light and they get light switched to them immediately, but for a very short time, but then that causes a disruption. I'm rambling a lot, but all these things, once you experience a lot of different things, you say, I would like to model that, I would like to understand this better. And there's commonalities between the different branches of engineering and problems that we solve. The bottom line is we have the amount of energy per bit to the noise power spectral density. This is something that Appendix A will go through, but that controls or defines the signal to noise ratio. And as the signal to noise ratio goes up, the probability of bit error goes way down. So that's just modeling the noise, and you're not going to do this in that much detail, but I just provided more background on it. So now what about in the PCM itself? PCM is also got a finite, has a quantization area because we're quantizing the analog samples into NB bits. So a calculation you're going to do in task 2 of this problem is you're going to look at the mean squared error under the different conditions of going through the channel. The first will be just a fixed amount of error that's always present between the output of the decoder and the input of the encoder, just due to the quantization effect into NB bits. But then if you make bit errors, this mean squared error, notice it's the difference. It's the squared difference between the output and the input. And by the way, the hat is not being used, or circumflex as it's called in topography, is not being Hilbert transformed. Frequently it's just used to mean an estimate. My velocity is v, but when I estimate it on my speedometer in my car, I call it v hat, saying it's an estimate of velocity. At any rate, it's the difference between the input and the output, and we square it. So it's easy to calculate. We can do it in Python, no problem whatsoever. So here's how we can give a run of analog samples through the PCM encoder and then decoder. And I'm not referring to sync words at all right now. I'm just assuming we know exactly where to put the words back together at the receiver. We get our analog sample back as m hat. And here's a function for doing an analysis on it. This function is called SNR PCM. So 1 over the mean squared error is like a measure of signal to noise ratio on the analog side of things, the analog input to output. So 1 over that MSE value, if you take 10 log base 10 of that, since it's already a squared quantity being error squared, that's what this function is going to calculate, the signal to noise ratio in the PCM analog samples. What is the quality that they have? So this function just sets up the entire simulation. It does not use the sync framing at all. It's just going to put it in a simple model to encode, add the additive white Gaussian noise, PCM decode, and then take samples of the input and the output, take the mean of the squared difference. So here I used mean from NumPy. Could use variance, but I just broke it apart to make it clear that I'm forming the squared error, and then I'm going to take the mean of it. So if you see this in here, and you'll be using this function, that wraps all that up very nicely. I'm estimating with n samples in this case, but this just manages all of that. However many samples I put into the input vector to the output vector, I just get 1 over the mean squared value, can take 10 log base 10 of that, and plug that in to an SNR quantization noise with bit error combination in dB. And then here I'm just giving an example of how you might conduct that. For this particular problem, which is task 2, I'm saying I don't want you to use one of our favorite speech vectors because I was playing with it last night. It was not giving me nice, consistent results. I decided to just go with a multi-tone message. Just got 3 tones in it at frequencies that are not commensurate with one another, or easily commensurate, and just run that through instead. And then as I plot these for different bit values, in this case, I want you to do it for 8 bits, and then I say do it for 6 bits and 10 bits, just to see the difference. You're going to get some sort of a performance curve which says as the input, as the signal to noise ratio in the link goes up, we eventually hit a plateau And that plateau corresponds to just the quantization noise in the encoding itself. But when we have bit errors present, we're going to get much worse performance. You can hear it and you can see it. So when you work this problem, I actually say, hey, go look at something up in chapter 8 that we're not covering, but there's a section in here. So this is referred to in the document, but bam, here it is. Noise in pulse code modulation. So here Dr. Ziemer does a complete analysis of it analytically rather than simulation-wise. You're doing it simulation. You're being kind of a real hands-on engineer that just says, I want to get an answer, I want to do a simulation. And you're going to see that's very common in industry. Theoretically minded people that have the time are graduate students, faculty, and so on, maybe in certain types of work scenarios. But here it's all done analytically, and then he draws a picture. So he actually, this is a MATLAB script, but he's doing everything analytically. Behind this script is all the theoretical stuff. But this is what the curves are going to look like that you're going to get. You're going to see that as the cylinder noise ratio in dB goes up, we get an increasing value in 10 log base 10 of the output signal to noise ratio. And remember, SNR in the output is 1 over the mean squared error. That's just a metric. Does everybody know what I mean when I say metric? Metric as in a measure of something. It reflects something. So the characteristic of this, though, is we reach a plateau when the channel signal to noise ratio gets high enough, and then we just see how it's a function of the number of bits we're quantizing to. So you'll just reproduce something like this. It's not going to look exactly like this, but it's going to be very similar in shape. And I want you to comment on it, that, hey, this looks pretty similar to this part of the book. And also, the for dummies thing is, go work a problem. This looks great to me, but I don't really know what I'm talking about. I'm going to turn this in, and then I look at it and I'm like, what? This is so bad. It's like, didn't you think about what you just did? So, once again, I'm giving you an opportunity to say, I can go look at something and I can say, hey, am I in the ballpark or did I make a coding error? So this is pretty cool. You just got to walk your way through it. So what can we do to protect the source error bits? We can do forward error correction coding, and this is done all the time in our communications, in cellular and in space and so on. So FEC is the term, and I talked about this 2 weeks ago probably. The Viterbi algorithm uses a convolutional, the coder is called a convolutional encoder, and then the decoder, which decodes from this trellis structure, is the Viterbi algorithm. And it's trying to find either the minimum distance or the maximum metric through the trellis to then be able to decode what bits produce that. I'm not asking you to understand the intimate details. I'm just letting you know that there's a lot behind this stuff. But in the Python module that I have for convolutional encoding and decoding, it's searching back through a trellis so many periods out, then it can stop and it can trace back and it can say these are the bits that must have produced the state that I was favoring when I look out in time. So it's called the traceback. It's called a survivor traceback path, and all of these paths here are the ones that trace back to a common branch, and that common branch in this location right here, that transition that made that branch transition is going to be the bit that most likely was sent. You might be thinking, and you probably are thinking, is AI involved with this somehow or another? Well, this predates AI, but AI is just a generic term, right? It's not amazing. Artificial intelligence is not without human brain involved with it, but it's just a tool. But this Viterbi algorithm is a what's called a maximum likelihood sequence estimator is what it's doing. what is the most likely path that it traversed based on what we observe a ways out in time. So the encoder-decoder operation gives you quite a bit of coding gain. This black curve would be without coding, and then with the rate 1/2 coding, the curves move to the left, which means that for a given channel signal-to-noise ratio, which is our EB over N naught, we get better performance. One fact, though, with rate 1/2 coding is that we send 2 bits over the channel for every 1 bit, say from the PCM itself. So our bit rate is doubled. And this means that if we want to keep the same signal-to-noise ratio, that's fine, but the energy per bit is now going to be 1/2 when we split it between one of the 2 bits. And we're also going to occupy more bandwidth because we're sending bits at a higher rate. I haven't really gotten too much into that, but if you send bits at a higher rate, it's going to occupy higher bandwidth, double the bandwidth, essentially. This is just some code that walks through setting up and using the functions encode and decode, and how you eventually collect bits coming out of the decoder. And I want to provide a little bit clearer indication of this in the Jupyter Notebook. So that's one of the things I'm still tweaking on a bit. So we've talked about task 1, task 2, with the mean squared error calculation, which is pretty much all laid out. Then task 3 is going to be this, and this is one that I was dreaming about this last night because I worked on it late last night, and then I said, I'm going to go to bed. And I first thought, I got to just get rid of this because this is going to be too frustrating. But I woke up this morning, I said, I'm going to give it a little bit more time to see if I can clean it up enough. But I propose an interesting scenario here for you to investigate and just learn from, and that is I'm going to increase the number of bits per sample to 14 bits in this system. I'm not going to encode that with a forward error correction. I'm just going to put 14 bits per sample, and that will increase my serial bit rate to 112 kilobits per second, not including what the serial or the sync pattern would increase the serial bit rate by. I didn't really talk about that either, but whenever you take a bunch of data that's your payload data and then you prepend it with a sync pattern, what are you doing? You're putting some what's called overhead on your data. What does overhead mean? If you work for somebody, it's the same idea actually. If you work on a project for a company, sometimes you have to charge things to overhead. Why would you do that? I'm just giving you an example. Where does overhead come in your work life?
Profit margin.
It's it's part of the profit margin, but it's like I'm doing a task that the customer's not paying the company for, but I still have to do something. I have to take a training class. I have to learn something new that doesn't pertain to the project. I just have to get brought up to speed. So you charged an overhead charge number. That's what I do where I work. But in the end, you get the payload is what gives you what you want. The sync pattern or the overhead that you might have on in a job is going to take up resources in the channel. So it's going to take some percentage. Here I've got 68 bits and 4,000 bits of payload in my first example. So it's a pretty small amount of overhead, but it's not zero. And you try to get good bang for your buck, and overhead is just part of what that amounts to. But in this calculation here, I didn't include any overhead due to the sync pattern. I'm just simply saying we're going to do 14 bits per sample at 8 kilobits per second sampling. But now let's consider what happens if we go with the rate 1/2 encoding, which is going to double our bit rate, but we're only going to do 7 bits per sample. So we're still going to be at 112 kilobits per second. So what you do in these intervening parts down here, and I'm not going to walk through this right now, but I'm just going to say you're going to look at operating the channel. So there's going to be a trade-off in there. You'd like to have the high fidelity. Well, you're limited to the 112 kilobits per second. Your ability to use the channel is capped there. You can't get any more throughput or any more bit rate through the channel. And you really like high fidelity, so you say, I'm going to go with 14 bits because that'll give me the best high fidelity quality in my audio, or PCM. But if I want to put some robustness into my system to handle the case of a corrupted channel with lots of noise, maybe I should go with the rate 1/2 encoder, which is still going to take 112 kilobits per second, but I'll have to dial down my bit precision to just 7 bits. So what you get to do down below here is you just get to listen to it, and I can see another typo. I had this set up for 16-bit PCM, but I'm doing 14-bit. You find out that if you have to operate at, say, only 60 dB channel signal to noise ratio, the listening quality is going to be much better with only setting out to have 7 bits of resolution, which is what telephony grade audio used to be. It would be 8 bits, but they have overhead, so 7 bits of PCM, let's say. And you get to see how this trade-off comes to be. 7 bits maybe is just good enough. It has to be good enough, because if you try to send all 14 bits, you'll get so many bit errors, especially on your MSBs. Remember, if the most significant bits get errored, you get loud popping and cracking sounds. So just trying to drive home how that factors into a given system. Does that make sense? I mean, my objectives are always to get you to learn something new, something that's not super obvious from everything in the textbook, but doing some hands-on experiments. So if I don't, can it, but I have to look at it again. The problem is, one of the things that's bugging me a lot, because the Viterbi algorithm is only written in Python, it's not compiled, so it's in a loop. Painfully slow. Even on a fast computer, it's still going to be very, very slow. So I have to assess that. I haven't really sat down because I've been running to do all kinds of other things. But if it survives, it survives. If it doesn't, it'll just be there, and it'll be something you can look at on your own later. Any questions or comments right now? I'm going to jump back over then to our notes. I'm going to set this up for the Jupyter Notebook. First example I want to look at is right here. I realize you're thinking this is a dual or triple moded type, triple threads that we're passing through taking a class. We have the homework thread, those tasks. Now we have these project tasks, which is another thread, and then you have studying and taking exams, which is your third thread. So it's not unlike other courses, though. You have multiple threads of activity that go within a course. So I'm just trying to load balance a little bit better. So some of you walked in late, so you didn't see the big innovating thing that I now have to help us stay on track. Is I have this important dates table that I'm asking for inputs. If you see something that's still not adding up, I intend to tweak this right down to through the end of next week before I leave, just so you can keep track of when homework's due, when projects are due, when exams are going to happen. So this takes us through the end of the semester. And for starters, next Tuesday, my last day to lecture for a couple of weeks, we'll be reviewing for exam 2. And I will be posting more stuff like I did before. Even though there were some not so good results on the exam, something just hit me in my head, so I decided I'll just talk about that before I get back into the lecturing. One of my plans is I had for next Tuesday is I'm going to have old quiz problems without solutions for chapter 3 and into chapter 4, okay? Like, remember how I did that? And then you're going to have, in addition to the chapter or the exam 1, which I've already posted, I'm going to post some exam 2s with solutions. So you'll have the same base plate to do your studying for. You'll be able to write another two-sided crib sheet for this exam, plus add in the existing math tables and stuff. And I guess I have to remember to bring the paper exams with all your crib sheets stuffed inside of them back, and I'll lay them out here and you can take your packet of paper back, because I don't want it anymore. It's kind of heavy to carry around, so it's sitting at home right now. So what I'm getting at, though, is that reasonable to assume that, or so some of you have, because you saw failure or not as good a work in the exam as you were hoping for, did I set you on a path that did not allow you to perform as well, and I should not do something, but I should do something else? I'm not going to give you the answers to the problems, obviously, but was there something flawed in that didn't work well? I mean, right now I'm inclined to say I want to do the exact same thing because it seemed initially to be like it was a good idea. Okay, so I'm going to go with that. But write to me on Slack if that's not making sense to you or you don't like that idea. It allowed me to write some exam problems that I could easily paste in from the quizzes, and I don't know if that was intriguing or not, or did that not excite you when you saw problems that you said, I've seen this before, I practiced it, I knew what it was. Did that work well?
Yeah.
Okay.
I just had a bunch of little errors.
Okay.
But it wasn't because of, I thought the material that you gave us was good to study for the exam.
Okay.
I'm just slow.
What's that?
I'm just slow.
Well, and this next exam will be at 9:15, so you don't have to be up bright and early, but as my table shows you, our final exam is at 8 in the morning on Tuesday, finals week. I can't change that because there's a class that meets in here, and I don't know what else is scheduled in here, and I'm not going to hang out to research all that stuff either. It's just not, there's so many dependencies. Some of you will probably have an exam later that day, and right? And you'd like to have time in between your exams. Nothing's worse, but maybe you've done it back-to-back finals. Has everybody done that at some time? Your brain gets fried a lot when you're done with the second one. I can remember first exam, fine. The second one, back-to-back, I was frazzling out, and I was not doing as well as I'd hoped because I just simply lost focus, the ability to stay focused. Okay, going into where we left off last week, we were looking at bandwidth of angle-modulated signals. So we started off by looking at the sinusoids, and we were looking at Bessel functions and the sidebands and everything associated with a sinusoid modulating, angle modulating a carrier. And as parameters change, the bandwidth gets wider. So then we drop down to, well, what is the bandwidth of an angle modulated signal? We could go with the fractional power bandwidth, which we got introduced to back in chapter 3 with that problem that I have to grade in set number 4 that I haven't gotten to yet. But that was finding and integrating the spectrum and saying you want 98% containment, so you define the bandwidth on the carrier as 98% of the power is in that band, and 1% is above and 1% is below in the bandpass signal. So that's a similar idea that what's used in angle modulation. So we go through and look at it for the tone modulation, and it works out to be this very first expression down here. At least this is the 98% one, and this is the one that I favor from the tables. It's the double underline in the tables that we were looking at last week, which you will have to make use of when you do the exam. At any rate, it's 2 times the quantity beta plus 1 times the tone frequency. That sets the 98% bandwidth, and the 2 is out in front of that because we're talking about a bandpass signal, so bandpass signal has a plus and minus side, the upper and lower sidebands. If it was a low-pass signal, it's always 0 to the band edge, and I'm pointing that out because when I graded the exams, I asked for the low-pass bandwidth, so that's half the width, whereas when it's a bandpass signal, it's the full width. So then a guy, Carson, came along and he came up with this rule called Carson's rule, which says that the bandwidth of a general angle modulated signal can be written according to this expression here, 2 times a parameter d, known as the deviation ratio, plus 1 times w, the bandwidth of the underlying message, whether it be analog or digital. And that w is a low-pass bandwidth, by the way. So deviation ratio is just the ratio of the peak deviation, which is fd from the modulator, times the maximum value of the message. So it's how far it pulls the carrier high or low with the analog message, and then divided by the bandwidth w. So that's defined as the deviation ratio. And that's equivalent to putting beta in for a single sinusoid, replacing it with d. Another way of looking at it, though, that if you write this out in light of what this is, we can call delta f the amount that we deviate the carrier with our message, and I'm speaking, leaning towards FM in particular, frequency modulation, how much we deviate the carrier. And prior to being in this class, you probably weren't thinking too much about bandwidth, but you were maybe thinking about a square wave modulating an oscillator, like a VCO. The input to the VCO would be a square wave, and it would push the frequency up on one excursion and push it down on the other. So if you were looking at the VCO, saying being at 1 kilohertz, push it up by 1 kilohertz, pull it down by 1 kilohertz, so you would say, oh, the bandwidth of that signal is going to be what? 2 times delta f. And that intuition is correct as long as w is much less than delta f, because you can see right here in this expression, in this way of writing out Carson's rule, the bandwidth is just 2 times delta f plus 2 times w. And there is a homework problem that you're turning in that kind of gets into this discussion. I guess I'd like to mention that too. I also want to give some hints on the bonus problem, but let's just go look at that problem just briefly so you know what I'm talking about. It's not in 7 though, it's in 8. So I'll leave 7 up there though, I'll open up 8. I'm drilling onto this problem because this problem number 3 is exactly this part of the notes we're going through right now. It talks about, or it says that we have a carrier. And why did the highlighting go on all of a sudden? I don't know. My mouse did something. At any rate, you're going to modulate a 100 megahertz carrier with a 10 kilohertz sine wave, and the maximum deviation is going to only be plus and minus 10 kilohertz away from the 100 megahertz carrier. So there's a fallacy in the reasoning, and I don't really want to drill into this that much because I'll give you the answer. It's really easy once you sit down and think about it. But the fallacy in the reasoning that the engineer has revolves around what we were just looking at right here. It revolves around this exact bandwidth expression. So if delta F is large compared to W, then it's safe to say it's going to be 2 times delta F. But if delta F is small compared to W, then W plays a role in defining the bandwidth, right? It's just that simple. This is not a really hard math concept. It's just the way it comes together. So that problem is kind of fun to work because it tests your understanding of working with this simple equation. So 2 extremes would be narrowband, where D is much less than 1, then that expression says B is just going to be 2W. And when D is much greater than 1, then it's going to be 2 delta F. Most systems fall somewhere in between, like FM broadcasting, which we already looked at, which this example pertains to, is somewhere in between. So in FM broadcasting, we have 75 kilohertz per volt for the deviation constant. Suppose the message is at 1 kilohertz. The beta value, which is this formula right here that we were talking about last week, FD over FM times A. A is 1 up here. It's going to be 75. So plug that in, and we see that delta F is 75 kilohertz. Plug that into Carson's rule, or use the exact expression for the Bessel function table, and it looks like this. Carson's rule and the approximation for the 98% bandwidth is saying it's this red dashed line, so it's covering 152 kilohertz. So 76 and 76 below, say 101.1 megahertz. Does that look reasonable? I mean, in terms of how the definition works out. Those of you taking the lab are doing this already in the, well, never mind. Lab 5, you'll be doing this exact thing, and you'll see that it's nice. It's an approximation. So then I further extend this. Suppose we pass this signal through an ideal bandpass filter, only 11 kilohertz wide, centered on the 1.1. So where's that 11 kilohertz? It's going to go up 5.5 kilohertz. So I guess I'll use my purple, which is in here. So that'd be the plus and minus 5.5 kilohertz. This is the shape of the bandpass filter. So we can go ahead and calculate that the input power in this example was 5,000 watts, and the power that comes out of that filter is only due to the Bessel functions that lie at the carrier and up to 5 sidebands either side of the carrier, so that works out to be 241 watts. That's just another calculation that shows up in some of the homework problem, but you look at this picture of the spectrum and you say, I believe that. I mean, it's supposed to be 5,000 watts, and what's contained in that purple rectangle is only 241 watts compared to the whole thing being 5,000. That looks about right because the sidebands tend to be more powerful at the edges in this case, so they rise up higher. This was the suspension bridge analogy that I have to it. And again, those of you taking the lab, you'll have fun because you'll be sitting there with a function generator and you'll turn it up, look in the spectrum analyzer, and you'll see this unfolding in real time. This is just a calculation problem though, but some of this stuff is in the homeworks. Oops. So now the next thing is, could we get an exact analysis for more than one tone in FM? And this is sort of a trivia question, but it's like somebody needed to do this, and actually this is used in ranging in satellite communications. They do something called multi-tone ranging to get distance. So they'll send multiple tones at certain frequencies and then receive them, and from that discern what the range to the satellite and back is. So somebody worked this out, and this is just a special case of just 2 tones. So if we have just 2 tones for the message, we have the corresponding indices beta 1 and beta 2. We go through the original analysis that we did with the complex envelope, the real part with the complex sinusoids inside of there with phase modulation beta 1 and beta 2, sine omega 1, sine, that's a typo for me, omega 2. So we can expand those out using a Fourier series expansion, which is the next 2 lines. And then we can put that back together. We can put these Fourier series expansions inside of here. And this is the awesome mathematics complexity that we can get to. We now have a double sum. When I say awesome, I mean a single sum is like you've got 1 coordinate, so you're just taking points along the line. But when you do a double sum, it's like you're summing over a matrix. You have a matrix that has an infinite dimensionality in both the x and the y axes. But it does roll off. But that's what this represents here with this double sum, to get the various sidebands at integer multiples of omega 1 plus and minus with integer multiples of omega 2. And you can again define a bandwidth based on Carson's rule, an approximation, and then I just carried this through, and I did this in Mathematica. This was a really long time ago that I did this plot, but it just gives you an idea of that you can handle more special cases for certain types of modulation, but it grows more and more complicated. So simulation is very handy. This was done analytically, but you could do it simulation-wise too. And we could do that if we wanted to today, I suppose. Okay, so stepping along the way, any questions on that? Because some of you may end up on a ranging project somewhere in Colorado Springs in particular, where you might see Bessel functions floating around. They do come up. So the next thing I want to do is just talk about trying to get another handle through simulation on band-limited noise, either PM or FM. So here, rather than putting up tones or a particular voice message, I'm just going to suppose that I'm going to produce a message which is band-limited noise. So here I assume the bandwidth is going to be W hertz wide, low pass, and I'm going to generate using the RAND-N Gaussian variates, and I'm going to control the Gaussian variates with a particular deviation ratio. And I jump into that down in the notebook here. So here I say I'm going to create a very high order filter to filter the white noise from the Gaussian variance. So this is the high order low pass filter. And then I'm going to drive that into this modulator as my M signal after it's been filtered. And I convert this to the discrete time domain to be a DSP kind of a problem. I'm looking then at the complex envelope associated with just the term that's right here. Oops. I can't draw on this in the notebook. But I take just this second exponential and just say that that first exponential is the carrier. I'm just going to ignore it and just focus on the complex baseband envelope. And then I convert it to the discrete time domain, and now I have my modulator looks like this, where I'm going to use to do that sum, which is a function of the index n. I get that action from 0 to n as a function of n by using the cumulative sum function. That is like the discrete version of integration with a sequence, or in DSP. So that's my baseband waveform. It has the cumulative sum in it, and then I will send that through, I will send the white noise through that. So I generate the white noise, then I filter it. I'm using a function that's available in Signal for a large high-order IIR filter. So that's what SOS filter is, second-order sections in ratios of polynomials in the Z-domain. And so SOS is just the filter structure that came out of the design of the filter. It's kind of incidental, but in my helper, IIR helper, I have it output the SOS coefficients. And SOS is second order sections. It's not I'm raising my hand saying I need help, I'm dying, you know. I'm just joking because SOS is a universal language, I think, isn't it? Anywhere in the world, SOS means I need help. So I pass that through and I get a Gaussian PDF. I just use the histogram just to see that it is indeed Gaussian, and I'm going to look at the amplitude of that, and I'm defining an amplitude level between plus and minus 1 as my approximate deviation. I think it was arbitrary, but it looks like it lands at about plus and minus probability density of 0.25. So I send that through and model its bandwidth and come to find out that it's based on the peak deviation, df, assuming I guess it's 1 sigma is what I assumed. It's 2 kilohertz. So now I'm going to plot the input signal to the modulator and the output signal from the modulator. The input is just the white noise filtered with the low pass, so it obeys. It's about 1 kilohertz wide. When I look at my modulator with that amount of deviation coming out, it's spreading out, and the red line there corresponds to my approximate Carson's rule idea for the bandwidth. This is actually B over 2 is what that would be, so it would be 4 kilohertz wide for this particular signal. But you get the idea that it is rolling off. It's not rolling off as fast as it rolls off on the input side as a result of the exponential modulation, but it is still, the bandwidth is getting limited as it goes up in frequency. That was just an intrigue factor for me, and it just tells you that if you have a pure noise modulated, band limited noise, you can get an idea of how much bandwidth it occupies without looking at spectral lines and things. You just have this shape out there. Now we can further take that sinusoidal FM modulator idea. In other words, this whole expansion idea in here that I went through to get down to this last line here tells me what the complex envelope looks like with angle modulation, and I can put anything I want in here for M of k. It can be a discrete sinusoid, for example. It could be 2 discrete sinusoids. So here, I just go forward with that, use the cumulative sum, and I'm just going to put up a message of cosine 2 pi FM 1, which is 1 kilohertz over Fs times n, and I'm just running that because I want to come back to it again. And then I go ahead and just use the PSD function, and I get a nice Bessel function spectrum. And this is supposed to be at 0 because I set this equal to 2.4048. If you remember from a couple weeks ago, this is where J0 goes to 0. Remember that from the tables? Remember that from the Bessel functions? I mean, that was plotted right up in here. J0 is this guy right here, and that's 2.4048 is right there. So that's pretty cool. That says we can modulate and see if I wanted to tweak this. You can see I had this set up for 2-tone modulation. Suppose I want to put in a second tone at 100 hertz and give it 2 rather than 2.4048. So all I have to do is take out that comment, run this again. It looks much, much different, right? Because I'm putting in a 100 hertz tone and then a 1 kilohertz tone. This is what we could model this theoretically like I was showing. And this, to me, this looks a little bit funky because I would expect to see a purely symmetrical spectrum, but I'm not. And I can't explain it exactly. I haven't really thought about it, but how would it be if I just bump this up, put it at 2000? Now it looks a little bit more symmetrical. If what I just did is true, no, I didn't do it right. Had it at 200, so now it should spread out more. The reason why it's not looking as nice and symmetrical probably is because I'm not using enough samples. I could jack this up to 1 million samples. And what did I not do? Didn't really change it at all. I'm not sure. This has got to be something to do with the Bessel functions, but it's not even symmetrical, which to me is interesting. This is what happens when you build models, though. You build models and then you get results that you just are puzzled, like I would have expected this, that, or the other thing. So what do? You have to ponder it for a while. I mean, I'm doing this in my work right now. I'm testing something that another engineer made, and I'm doing some tests on it, and everything's working well, but I have a little bit different factor in scaling for some scenario, and I'm just pondering it. I think it's probably correct, but in a simulation model, you have to be just vigilant about checking and understanding. And to me, since it's a model, what you can do is you can play with it. You can jiggle things around and just see if you're noticing maybe what's going on. In this case, notice when I took this back to 200 and it did get a lot more symmetrical than it was at 100 hertz. 1K and 100 hertz, and then we did 1K and 200 hertz, and we get this. So what is the bandwidth of this signal, this simple integrity test? You might say, because I have this set at -100, that must be the bandwidth, but you know, I can always fake you out by just trimming the axes, and so now it's narrower. What's the real bandwidth? It's gonna have to come back to something like a 98% bandwidth or whatever the customer would want you to provide. But one of the things with spectral plotting is I never want to do is just simply turn off the scaling, and then I'm going to see some other artifacts from the simulation and the FFT processing. Minus 250 dB is just not anything that we really want to think about. It's so tiny. So don't ever give me pictures where you just auto scale everything, because that can be very misleading. It makes you look bad to your manager who's like, give me something realistic. So don't just let it all fly like that. So I generally will plot, and then I will tune it a little bit, and instrumentation in the lab can go down to 100 dB, but still the bandwidth is going to be somewhere in here. And we could integrate it just like you did in that homework problem weeks and weeks ago. So now we're going to get into demodulation, and we'll take the break, but this is, to me, far more interesting than modulation. Modulation is pretty straightforward. I was testing a modulator yesterday that another engineer made for the LunaNet project, and now I'm back on the receiver again, though, because that's where the interesting stuff is. And in our study right here, we're going to be looking at how do we demodulate an angle modulated signal. We know with AM, we had to have a coherent modulator with double sideband, And then with AM, we could do an envelope detector. We're going to follow similar investigations with angle modulation here. We're going to start off with a formal discriminator. We're going to look at a DSP implemented discriminator, look at some analog circuit design ideas that have been around for ages and ages, and then we'll get into the phase lock loop for demodulating angle modulation. Phase lock loops are very common, so we'll be studying that. Right now, though, it's about 9:30, so how about 9:40, 9:45, somewhere in there. There's very few of you. Maybe nobody's hungry right now and they want to just sit here or go to the bathroom, whatever you need to do. I'm going to stop the recording and then restart it. Okay, we're back from break, and one of the things I want to do, because we're talking about what's going to be happening when I'm gone, and this table was on my mind a few days ago over the weekend. I just said I had to do this, and I hope, like I said, you will bring things up and that it will improve the quality of this table, because I want everybody to use this as a reference, like where are we going to, and what's happening. But what I want to do is talk a little bit about one of the bonus problems. And I also want to say, while I'm navigating to that, that what I want you to do, if you turned in homework last week and were just defiant that you wanted to get it in a week early, but I wasn't really excited about that, take anything back. And like I've said to some of you that are in class today, if you push anything out there and then want to renege on it, you and I both have the priority on the direct channels of deleting something. And just delete your stuff, because I get confused frequently. It's like, which version is the one I should be grading and downloading? So what I ask you to do, if you submit a new version of your homework, just please delete the entire old version, because I don't want any remnants laying around. It's very confusing to me. So take the initiative to go delete it. And I think it's in the drop-down 3 dots menu that comes up over a attachment or something in Slack, just to delete it. So what I want to talk about a little bit, and I gave you a link to the Modern DSP, but on this bonus problem with the SDR and setting up an IF near 10.7 megahertz, I was looking at my solution before class, and then the hints page is also up there. But just to refresh my memory, for that particular problem, what I say in the hints page, you have three variables to deal with in this problem. The bandwidth is set, but what you have freedoms to choose is you have to come up with a value of M that will work for the bandpass sampling. The exact sampling rate is you're free to choose, and then the IF frequency, we'd like to have it at 10.7 megahertz, but it might work out better to be slightly above or below that. So that's why I say near 10.7 megahertz. So besides the hints that I gave you on this problem, I'm just going to look a little bit at what I did in the problem myself, because I ended up resorting to Python to do a little model of what some of the possibilities are. So I'm going to try to draw something. So I'm going to see if my rubber tip will help me do anything decent. So the first thing, oops, that's going to work. I didn't want it to work just yet. First thing I did was I took this equation right here. Are any of you looking at working this problem? Because it's interesting and it's worth bonus points. So I took this expression. Whenever you have an absolute value, it's generally can boggle your mind until you unwrap it. So what I did for me is I said, I'll just reset itself because I had it set on eraser. So I wrote it like this. I said, let's expand out that absolute value sign, and then we have two working solutions that we can go after. We can rearrange this further. To look like this. If we rearrange it, we have two solutions that we can go after, and you want to get FIF close to 10.7 megahertz. So I set up a simulation, and what I did in my simulation was I set up my simulation to just play with this equation where I let M range from 26 to 32, and then I just simply plotted the two solutions for FIF. The FIF you see right up there in the upper right-hand corner. I let M range from 26 to 32, and then I used a print statement in Python, and I just printed what the different IF frequencies would be from that solution as I span from 26 to 32, and I get an idea then of where I get a pretty good solution that works well. And what we're doing here is we're constraining the sampling. We're constraining things with the fs/4 frequency that we want to convert to. So I did all of that stuff, and I actually tried, I did this for fs equals 0.4, and that's because we know the bandwidth of our signal is 200 kilohertz. So bandpass sampling theory says that we have to sample at greater than twice the bandwidth of our signal approximately. Low-pass sampling theory says we have to sample at greater than twice the highest frequency, but if it's a bandpass signal, we can most often get away with approximately 2 times the bandwidth of the bandpass signal. So I tightened it right at 0.4, and I got some answers by doing this approach here, and then I relaxed it even more and said I want to have some guard bands. So I said set fs equal to 0.5 megahertz. This is megahertz. And then I'll have some guard bands around it. So when I do my plotting, I'll get a better picture. And then I did the plotting down in using the plotting tool that I have in the Chapter 3 Jupyter Notebook for bandpass signals. I just used that setup with the appropriate numbers entered in, and then I get a picture. So I'm not going to give you the answer, but I can blow it up on my tablet here and just show you what it looks like. So when I picked the 0.5 megahertz, and then run the simulation, you can see that the translate, one here, one there, and then this one, the lower one, is at the 1/4 of the sampling rate. So it's at 0.125. The orange line in here is the 0.125. So I didn't get an IF of 10.7, but I got pretty close to it, and it just allows you to kind of play around with it. And I created a triangle shape just like I did in the Chapter 3 Jupyter Notebook. So that, it's divide and conquer. I mean, how are you going to solve a problem that seems to have 3 independent variables, and how do you go after it? You have to kind of break it down. And like I said, I used an iteration, and I'll just show you what that looks like when I run that iteration. I see I have this printf statement that's giving me what the options are. It's saying this IF or that IF works with m is equal to 20, 21, 22, 23. And I look at all those different numbers, and I look at which one's going to get me closest to 10.7, because I can't write a single equation to get that. Am I making sense? You have to have looked at this problem, otherwise you wouldn't know what I'm talking about. You're kind of iterating on it a little bit. So you have an analytical form, and then you go in and have the Python code draw you the picture like I showed you, and then you'll see, yeah, this can work. And that's that evidence. You got to give me some evidence to look at when I grade your paper, but that evidence will get you the 20 bonus points. There's not an exact answer. You just have to work your way around it. You might not pick 0.4 FS. You might go with 0.45 or something, halfway between 0.4 and 0.5. 0.4 is just too tight, though. I mean, that would be perfect. But FM broadcasting is not exactly up to 200 kilohertz, so it has a guard band already. You can do the analysis there, too. I did it twice. I did it with 0.4 and 0.5. So that's pretty nice, I think. We talked about how to work this last problem where and that's in the Chapter 4 Jupyter Notebook, where you can create this piecewise function, and then you can integrate it using cumulative sum, and then you can get the frequency deviation from the phase deviation, and you get those plots for this particular waveform, and do exactly what I say, only for the top waveform. Don't do it for all 3. I'm not asking for that. And honestly, I'm getting a little bit irritated at the fact that people don't follow directions very well. It's like, just do what the problem says. Don't do more. Don't do less. Don't do the wrong problem. That has happened too many times. Just do, what I'm asking for. Any comments or questions? And, soon you'll be on to set 8, of course, and that forms the bookmark, or the whatchamacallit, I can't even think of the right word, stop for the bookcase or whatever for the exam, where we're going to stop. We're not going to go all the way through Chapter 4, obviously, but we are going to be all of Chapter 3 and then portions of Chapter 4. So without further ado, we go back to Chapter 4. We did this noise example. There's a homework problem on this, which is not required to be turned in, but I thought I'd just talk about this a little bit. This is the idea of narrowband to wideband conversion. And this is something that is in the analog modulation domain. It's not, I don't know of it being used in digital modulation really at all, but it is a technique, and it was a technique that dates back to analog transmitters, analog FM transmitters, or where you want to create a narrowband signal using a simple phase modulator. And what was this modulator? It looks, if you remembered way back at the start of this chapter, it was this picture right here, narrowband modulation. That's what the narrowband FM modulator does. You just have to be able to have 90-degree phase shift. So RF components can do this. We have something called the quadrature hybrid. that you can rotate by 90 degrees, so you can generate sine and cosine, and then on the carrier, and then a multiplier, and then an adder, and this creates narrowband phase modulation. So this would have been a technique, or is a technique, that can be used to do this stuff. So then down here, what's going on in this picture, it's legitimate angle modulation. It's just got a very small deviation on it. You may choose to go through a frequency multiplier, and then the frequency multiplier, what it's going to do is it's going to multiply the carrier by n, and those of you in the lab know about multipliers because you've been using them in the lab, right? You have the RF multiplier on the board. And then it takes the whole argument, so it multiplies phi by n. So this is how we take and get our deviation ratio increased by this multiplication factor. Well, the carrier might have been a convenient carrier for generating the narrowband modulation. You then have a final frequency translation to take what comes out of the multiplier and move it to a new location. And I think where this idea first appeared to me, or something I saw either in amateur radio or in commercial FM broadcasting, you would create a very stable reference source, and then you would do some frequency multiplying and up conversion or final translating. So this is just simply to frequency shift. You're not going to change the deviation. The change in deviation here comes about through this factor of n. And that's what it's all about. So now on to angle modulated signals, or demodulation, I mean. So what we need is what's called a discriminator. And for FM, this is the way it's generally talked about. For PM, you can use a FM discriminator followed by an integrator. We'll see that. But for PM, if it's digital PM, you might use something else. But discriminators are quite popular in this domain. They're called discriminators, even though they're in the DSP domain. But originally they were purely analog. So we have an angle modulated signal, phi of t. The ideal discriminator comes along, and through sort of circuit magic, you could say, what it does is it's able to jump in and take the carrier and differentiate the argument. So you get d phi dt with the ideal discriminator times a deviation constant, or kd, capital KD for the discriminator, and then there's a 1 over 2 pi in there, so what you're left with is the FM modulation. So if you put in FM, differentiate it, you get back out M, and then you get the deviation constant of the discriminator KD. So this is what the ideal discriminator does in terms of converting an angle modulated signal back to the message. And if it's FM modulation, it's exact to within a scale factor of KD, which is the slope. So it takes deviation going on the horizontal axis and converts it to amplitude values on the vertical axes, which is converting frequency deviations into amplitude deviations. Sounds really simple, right? How do we make this work with a real life circuit? This is an abstraction, it's just a concept. So the PM case just throws an integrator at the end to get back the integral of the derivative of the phase, so it gets back the frequency to within a constant, or the phase to within a constant. So this is just the other half of it. But how do we approximate the ideal discriminator? Well, one approach, and this is kind of a motivation behind analog designs at least, is to just come along and differentiate the analog signal that comes in and then follow it with an envelope detector. So how does this operate? We have calculus, right? Why do we have calculus? Because calculus helps us solve all kinds of engineering problems. We originally got by, and we get by later in life if you want to abandon calculus with it, perfectly fine. But we can take the derivative of a function of the function that we're interested in differentiating. So we have, trying to think what's the right term, not total derivative, but I'm trying to think the calculus term for it, a function of a function. So we're going to differentiate this, we're going to operate on it, and we're going to get minus AC times omega c plus d phi dt, and then we have sine. This is taking the total derivative. Maybe that is the right word. I'm losing, not remembering my calculus terminology. But at any rate, inside of here, we see that our carrier has changed to a sine from a cosine, but the important thing is this guy right here is what we're looking for with our discriminator. So is it situated properly? Well, you look at this and you say this looks an awful lot like AM modulation, because in AM we have a constant, and here we have a constant omega c, assuming that that's stable and staying fixed. And then we have the d phi dt sitting there. So this looks like amplitude modulation, provided that the envelope doesn't go over 100% modulation index. And this is reasonable. D phi dt should be less than omega c. Otherwise, you're really modulating like crazy. You know, you're deviating like crazy. So we can use an envelope detector, and the envelope detector would get us back to within a scale factor that now depends upon the amplitude of the received signal, the FM message. And if you want a view of it in terms of the ideal discriminator, it's this. 2 pi times AC is the scale factor from this total derivative differentiation. Now there's some bad things that happen with this. Noise gets differentiated and interference gets differentiated. So what do angle modulation schemes generally do? They're what are known as constant envelope, because there was never any modulation outside the cosine carrier. It's just a constant carrier amplitude. So we can go ahead and pass the received signal through a limiter. A bandpass limiter is just limiting the amplitude extremes to plus and minus something. That's what a hard limiter would do. And then the bandpass filter does what's called a zonal recovery, and it's taking the zone around the original carrier and just bandpass filtering it, because there are going to be harmonics produced with the hard limiter, but the bandpass filter just gets out the frequency zone, as it's called, of the original signal. And now we can come along with our total derivative ddt, and then follow up with the envelope detector. So in FM broadcasting, this is used extensively. It's what happens when the signal arrives at the receiver. It goes into a limiting amp through a chain of intermediate frequency amplifiers. And that limiting amp keeps the amplitude of the carrier constant so that it doesn't interfere with the envelope detector. And it also suppresses any interference or other things that would normally be an issue with amplitude modulation. And in growing up, having a father that did amateur radio, I was keenly aware of these things because he would always point these things out to us. Why? I don't know. That's kind of a prerogative of being a father, right? You get to teach your children things, your things, and your wife teaches them other things, right? So you've had that most certainly in one form or another, but cars, notoriously, when they were older, they had mechanical ignition systems. The points are opening and closing in the electrical wiring to fire spark plugs and so on. So you would get ignition noise, and if you're listening to AM radio and the signal was weak, you would hear this popping and cracking sound going on because of the ignition noise. Chances are none of you have experienced that, but it was brought up to me, and actually if you were an auto mechanic and liked working on cars, you might notice that and say, oh, I've got a problem with my car's distributor that's distributing, the voltage to the various spark plugs. Everybody knows that at least, right? Somehow or another you have to set the order that the plugs fire so that the cylinders get their explosion and make the engine actually run around. Good question now. Will that soon become, nobody understands that anymore, with an electric motor instead? I don't know. It's intriguing to think about that, right? It's called IC. Have you ever heard that term before? Internal combustion. That's like a really bad word anymore these days. It's like we're in the old technology of internal combustion. We're exploding fuel, putting gases out. And I went to a Python conference, and a guy, mechanical engineer, his whole Python modeling was for getting the efficiency of an internal combustion up even higher. And interesting to think about, I think. At any rate, so the limiter suppresses noise. It will clip the envelope of the carrier so that if there is any interference that came about due to ignition or other incidental things in the signal space of receiving, it clips that off and it makes it quiet. And that's what makes FM so wonderfully nice. It has a shh sound when it's not really strong, but it goes into what's called full quieting when the limiter can fully turn on and it can do its thing. So we can approximate, and this is heading towards the DSP side of things and also analog, we can approximate the differentiator with a delay and subtract operation. So we could take two copies of the signal, one delayed and one not delayed, and we can then think of having tau in the denominator, and we're approximating the derivative. So a discrete time implementation we're going to look at next is just taking and using that idea of a differentiator as being a forward difference, let's say, or backwards difference, I mean. This is called backwards difference because it's causal. It takes the present value and one sample in the past. So it's called a backwards difference. So here's a discriminator that I implemented many years ago, and maybe it's unique. I know it's not, but I just came up with it a long time ago, where I would take a complex signal that has real and imaginary parts, form the backwards difference for the derivative in this operation here. This is A and B polynomials in our filter function. And then we have approximate to the derivative of the y part, which is called the quadrature or imaginary part, and then x is the real part, and then we divide by this. Now that doesn't make sense until you actually jump into this, and in lab number 6, where you're doing things in DSP with a software-defined radio, this gets explored fuller. So those of you in the lab will see a more detailed version of this and what the limitations of it are. But suppose we have the complex envelope signal, which is what we were looking at earlier over here in Jupiter. Bounce back up to it right here. When he did this study originally, we didn't have this extra signal in here, so let me just turn that off for a second so I can get back to where I was. Put the comment back in here. Not go all the way up to 1 million samples. So we have this is at baseband, so this has a real and imaginary part. So we can now operate on this with this discriminator over here in the notes. What I do is I say we want to take the complex baseband discriminator and just take the derivative of this phi, and phi is now has a real and imaginary part. So phi has got in phase and quadrature parts, and so we get the angle of it from the angle, the arctangent of xq over xi. Standard trig, right? So now that's our phi, and this would be viewed as a 4-quadrant arctangent. So it's a real arctangent as opposed to the simple one, doesn't get all the quadrants figured out right. So it'd be a 4-quadrant one. An angle in Python and MATLAB does what's called the 4-quadrant arctangent. At any rate, to differentiate that, go with the calculus formula for differentiating an arctangent function, and this is exactly what I get from that formula. So I get xi times the derivative of xq minus xi derivative times xq, and it's normalized by xi squared plus xq squared. So these derivatives here and here can be done with a backwards difference of the I and Q signals. And then this is just a normalization. And this normalization actually is kind of like a limiter action, because you're taking the magnitude of the in-phase quadrature and adding and forming it. That's what that denominator is. It's like the magnitude squared of a complex number. So I can feed that in. And here I've just set up the model again in the simulation here in the notes. But it's the exact same setup I was doing in the Jupyter Notebook. And then I come down and call the function that I defined earlier in the notes, the discrim function, which takes the complex input. And that we just saw in the notebook, but here's what the discriminator output is. You look at that and you say, I want you to be able to say, wow, it comes right back again beautifully. Kind of cool, isn't it? Now you find out in the COM1 Lab 6 that this doesn't work for all amplitudes. If the deviation gets to be too big for the sampling rate, this thing sort of starts to break down. It doesn't work. It doesn't have infinite dynamic range for frequency deviation. But in a limited range, it works beautifully. It works perfectly, as a matter of fact. So I could go off and explain that in the notebook, and maybe I will, because here it is right here. This function is not in any Python modules right now, except it will be in a code bank for Lab 6, but I haven't pushed it into the code base. So see here, I just generated the angle modulation. Then I'll run it through the discriminator. I'll run it through the spectrum and then run it through the discriminator. And there it is. And another nice thing about the discriminator, it will be sensitive to frequency. So if I put a small deviation on this in the modulator, I put a small amount of carrier in here, which I can do by, say, setting this equal to 100 hertz. The output of the discriminator, what it does in the frequency domain, all it's doing is you seeing it shifting it to the right by 100 hertz, so it's not centered anymore. But the discriminator is going to faithfully reflect that too. I don't know if you can see it, but it's shifted up. It's now on a pedestal, so the discriminator is picking up the fact that there's a frequency deviation constant above 0. And if I push it harder, maybe put this at 500, you'll see it even more obvious. You'll see it here first. Here it's now obviously shifted up, and here the discriminator is definitely shifted up above the baseline of 0. So if you DC couple this discriminator can be used to drive a tracking function, or it can be used in what's called automatic frequency control. It can adjust something to counterbalance that if you want it to. It's called AFC, automatic frequency control, in a radio. Or it's called a frequency tracking loop if you've put it in a feedback system, which is somewhat different than a phase lock loop. Phase lock loops track phase, whereas frequency lock loops track frequency. Now, stepping back in time, though, here's what analog circuit implementations have done over the years to get at a discriminator in analog electronics. First is just a high-pass filter, and there's a homework problem on this that is a bonus problem further down the line here. It's one out of the book, but it starts, rather than with a high-pass filter, it starts with a band-pass filter. Same idea, though. The idea is that you have amplitude versus frequency changing, and this technique is talked about in Lab 5. It's called a slope detector. So you have a filter, in this case a high-pass filter, and if the analog signal comes in somewhere in this approximately linearly changing amplitude response of the high-pass filter, the signal deviates back and forth with the FM here, and it causes the envelope fluctuation to occur. And because you've got carrier sitting at FC all the time, you get some output voltage and then it gets bigger or it gets smaller. So the idea of it being called a slope detector is that it will convert FM to analog modulation, which you can envelope detect. And the slope detecting is how it's working. It's the slope of the amplitude response of the filter, which is got a time constant much, much smaller than the modulation itself. So it almost instantaneously responds to give an amplitude fluctuation. Is this making sense? We're converting FM to AM, and then we can use the envelope detector. So when Armstrong invented FM back around 1900 and started becoming popular, low-cost receivers could be made that were not that much more sophisticated than the envelope detector. This is a high-pass design. If you're at 10.7 megahertz, you could use a pair of filters to build what's called a balanced discriminator. So here you have two tank circuits, one tuned high and the other one tuned low, coupled in through a transformer. Then you have envelope detectors operating on each, and what you're effectively doing is you're combining the slopes of the high and low tuned filter to give a wider linear region, and this is what broadcast FM would have done before doing things with phase-locked loops. So this is the double balanced or balanced discriminator idea. In Lab 4, which is you guys are working on right now, I use an FM RF chip there, and it has another type of detector called the quadrature detector. So the quadrature detector looks like this. It has a resonant circuit at an IF frequency, typically, and then it's got a multiplier, and it's got this setup where it's got a direct path into the multiplier, and then it has the capacitor, which gives you a 90-degree phase shift in combination with the changing phase and amplitude response of the tank circuit. And it's called a quadrature detector because you've got quadrature signals feeding the multiplier, one at 0 degrees, the other at 90. This was an invention, I don't know how long ago. It's not 1900. This is much more modern in terms of how to get at angle demodulation with a quadrature detector. So if you look on the board for the lab, you'll see that there is a tank circuit on there. It's the quadrature amplitude detector tank circuit. It's in a metal can and it's tunable. Capacitor is fixed in this case, and then there's a ferrite core that goes up and down to change the inductance of that side. So I walk through it bullet-wise, and then I walk through the approximation in math. And I'm not going to go through. I don't want to go through the details, but there's constants in here, K1 and K2, that are related to circuit parameters. And when you choose those properly, you get the right dynamic range, frequency deviation-wise, and amplitude response-wise, and you end up getting back to your message with a constant KD, and then K1 and K2 show up in there too. So this is what the Lab 4 radios do, and a number of you worked with the radios now. They work pretty good, right? You receive local stations, you're learning about frequency translation, but it is a quadrature detector that's being used in there. So then that brings us to the next level, and that is a feedback demodulator, which uses a phase-locked loop. So we can directly demodulate FM, and it's also a basic building block in communications type work, the phase-locked loop. It shows up, the stuff I'm working on, there's tracking loops for frequency and phase, and then for symbol syncing. And symbol sync, after it leaves there, it goes to sync pattern out of the bit stream and so on. But all of those use tracking loops, and all of them have to use tracking loops because we don't have perfect knowledge of either clock frequencies for the data bits or the carrier frequency because of Doppler. and just uncertainties between transmit and receive. And it doesn't matter whether it's space communications, it might be the Doppler due to the spacecraft creating Doppler as it comes to the Earth or goes up. But think about any device you have like this Bluetooth mouse. There's a crystal in there probably, and then in my laptop there's a clock frequency, and it has to be able to lock up and do some tracking. And the oscillators are not, they're like 100 parts per million or something, maybe 10 parts per million of stability. So you have to make up for those differences by having some sort of a tracking loop to deal with that. It's wonderful, right? I can say that with a smile because it's what gives a communications and signals person work to do. The layman who just says, make this, and walks away and says, you make this for me and I'll pay you money, doesn't understand the details to make it work. So as engineers, what do? We have to tell them that we need this, 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 and this, and oh, this is going to cost some money and it's going to take some time to get this working properly. And they might get upset with you, but you say, well, okay, thank you. I won't be doing work with you then. You don't get something for nothing. Okay, so what about phase-lock loops? There's a lot of different configurations. It's sort of an amazing device, and when you come out of a Com1 class, you have enough knowledge to be somewhat versed in phase-lock loops, but you do, and you also have a good appreciation for the fact that they're not trivial. They're a little bit wily to work with. They're not a nice, simple linear feedback control system all the time. They'll be approximated with that, which gets into what Dr. Platt would have taught you last semester in control systems. But then this also has a nonlinearity in it, which makes it definitely more challenging. The nonlinearity has to be there. You can't linearize it and have it manage acquisition. So the basic building blocks are the phase detector, which will be the nonlinearity because fundamentally it's this type of an operation. There's a multiplication going on in there. A loop filter, which will be either passive or a digital loop filter, if it's a digital phase-lock loops. A loop amplifier, some sort of a gain block, and then a voltage-controlled oscillator, which would be an analog circuit in a lot of applications, but then in the DSP-based solutions, it's called a numerically controlled oscillator, where it runs with a digital analog, a DSP waveform going in, and then you have a clock controlling an accumulator, and the clock makes that accumulator accumulate up, and then it rolls over and starts again, and then it rolls over, pumps back up and starts again. So it produces a VCO type output, but it does it with a digital word. So you might use a 32-bit length register in a clock frequency of, I don't know, maybe 100 megahertz or 10 megahertz or something like that. There are equivalents, and going through the analog phase-lock loop is a good way to get started. And then we have the models, and we actually have, I'll just dial ahead so you don't think that I'm going totally crazy. In Python here we have Scikit DSP.com has a module called synchronization.py. So I've got some of the phase-lock loop types of algorithms are built up inside of that. And I did not set out to do that when I first started using Python, but then I said, because I taught this class, I taught Com2, I taught other classes that use phase-lock loops, and then I actually taught a whole course on phase-lock loops, so I had a need to develop that more. So the basic building blocks are, we have a received signal that has some unknown phase, phi of t, in it. We have the output of our VCO, which is perfectly at quadrature, but it has a phase deviation of theta. And frequency error is actually wrapped up inside of phi of t minus theta of t, because we know that if we take the derivative of that and divide it by 2 pi, we get the frequency error. So what is the phase-locked loop going to try to do? It's going to try to drive the frequency error to 0, which it will do to lock, because it can't not have it at 0. And it will try to get the phase error to be as small as possible. Ideally, it will be at 0 as well. So that's where it gets the name phase-locked loop. So we'll assume a sinusoidal phase detector initially. So this is the output of the sinusoidal phase detector. That is what this guy is right here. And then it's got some gain constants on it. It's got 1/2 AC AV. That comes from just two sinusoids being multiplied together. Actually, it's going to be, AC cosine times AV sine. One of the trig identity terms will be 1/2 AC AV times this. But then we also have a detector constant KD, and that is inside of here. So there's a KD inside of there. And in lab 5, you will be doing a phase-locked loop for those of you in the lab, and you will be characterizing what is KD by doing an open loop measurement. For the VCO, we have this idealized relationship, and in lab 5, you'll use a VCO made out of the function generator, which is perfect, absolutely perfect. Those of you in the lab, remember you've already used the back terminal on the generator, so you have a VCO input port effectively. So you use that as the input, and then you set up the function generator, or you buy off the shelf a VCO from Mini Circuits or someplace like that, and you've got an oscillator that has some quiescent frequency, omega naught or f naught hertz, and then the deviation d theta dt is controlled by the gain constant of the VCO, how many megahertz or hertz per volt, and then the amplitude of the input. So you can write it as instantaneous frequency, or you can write it as instantaneous phase, whichever way we want to work with it, and we're going to do both in the modeling. So now we've got this for our model for the phase-locked loop. We've filled in more details. We're going to work with it at baseband initially, so we're just going to assume that we have baseband signals. We have phi coming from somewhere. It ultimately will come from inside the argument of the cosine, but right now we're just going to treat it as if it's a baseband signal, phi. It goes into a differencing block, and that's the action of the trig identity. So it'll be phi minus theta, and then it picks up the nonlinearity of the phase detector, which will be sine. And then we have the loop amplifier, which will incorporate the detector gain and the amplitudes of the two inputs. So those are all combined together in that block. And then we have the loop filter, which has some impulse response. The notation here is the book's notation, so I probably would not have picked F, but it is what it is. Actually, in phase-locked loops, F is the most common loop filter variable name. So that's the impulse response. Initially, what we're going to do is we're going to bypass this and just make what's called a first-order loop, so we won't have any loop filter in there. And then we have the gain of another amplifier. It could be the loop amplifier, whereas these gains over here are pretty much tied down. These represent the amplitudes of the input, the VCO output amplitude, and then KD is associated with the phase detector itself. But we might put an additional gain in, and this could be done, say, in the lab with an op-amp or something, to gain up what comes out of the phase detector and then drives in to the VCO. But again, the VCO is going to output a cosine of some or a sine of something, but its argument is going to be theta. So here we're just modeling that it's kV, the VCO gain constant, times the integral of the input. Because the VCO creates a voltage, a frequency response, a frequency shift due to voltage, but then the phase is the integral of the frequency. So we have that integral in there. So what do we have to do to show tracking? Here's all the gain constants piled together, so just keep them in hand by just saying KT. So now we can sit down and say, what is the output of the VCO? It's going to be KT times the integral of the sine of the phase error, phi minus theta. Or if we differentiate both sides, it's going to be the derivative of the phase of the input equaling KT times the sine of the phase error. So what the book likes to do, and what I'm following suit with, is I'm going to call the phase error psi. And then what we're going to do is we're going to apply at the input a frequency step. So we're going to set, this is the input right here, so it's turning on at t is equal to 0. It's been sitting quiescently, sitting all happy and everything. The phase lock loop is locked, actually. And now we're going to jump its frequency by delta of omega radians per second. So what happens is d theta dt, which is this equation up here, is going to take on kt sine of t. But we can also get at the d theta dt as delta of omega minus d psi dt. And this is where things start to get confusing. And I admit I've got two things going against me. It's the end of the period, so you're getting fatigued, and it's just plain not super easy. It's something that you just have to get your head wrapped around by staring at it for a while. So what Dr. Ziemer decides to do, and what I've done in the notes here, is I'm adopting the use of the phase plane plot. So the phase plane plot takes quantities that are in the above equations and puts them in a 2D plot. So you're going to have psi of t, which is the instantaneous phase error, and then you're going to have the vertical axis will be d psi dt, the instantaneous frequency error. So what I really like about this is that everything is right here, and you just have to accept the fact that the blue curve is what's called the phase plane of the phase lock loop when it's just sitting there getting ready to try to lock. So it's the operating curve. It's kind of like in differential equations, and my memory doesn't serve me really well on it. You learned about general differential equations. You would get an operating characteristic of how a differential equation worked, and you might plot, one variable versus another in a differential equation. So here we're plotting two of the variables that show up inside the argument of the differential equation, the phase error and the phase error derivative. So, and what you can do to understand how this works is, initially, when the loop starts, in this case, it's sitting right here. And this occurs at t is equal to 0. It's sitting right there, and this blue curve is totally down, and it's just passing right through 0, and it's just happy as can be. It's sitting there locked. It's going to stay there because there's a restraining force here and here that if it tries to go above with a frequency error or go below with a frequency error, it says, nope, I can't do that. The feedback in the loop is going to be such that it holds it in place. And how does feedback work in general? And you discuss this in electronics, I think, too, but the idea of feedback is if you try to go one direction, the feedback action brings you back. If you try to go the other direction, it brings you back. What's a good example of feedback in your everyday life? Maybe it's your seatbelt, I don't know. The seatbelt is trying to hold you in one position. You try to go forward, it won't let you. Try to go into your seat, it won't let you because it pushes you back. So what's a better example though? Okay, driven, and then get gravity involved as part of the feedback maybe. I don't know, I'm just trying to think of something else.
Flying the compressor.
Okay, it's going to keep things at a constant level, compression level. We do compressors in this stuff too, but we're not talking about that. But at any rate, it's sitting right there at t is equal to 0. So now at t is equal to 0 plus, which is the next point up here, it jumps up to b because we've given it that step, which you can just see at the top of the page up here. Given it that step of delta of omega, so it jumps up, and the phase-lock loop operating curve is now the blue line exactly, because we've changed it, because we've got this in place now. So things are out of equilibrium. We can, this right here is telling us the story that is part of the equation. Maybe it'd be better if there would be something around that, I don't know. We can get our phase plane plot from that, exactly. That's what's happening. So it shifts up by delta of omega, and the loop is not happy. It's going to say at this point, it's creating an error signal that's going to drive it back to 0. So it's going to head down in this direction, and if it tries to go past this direction, it'll be forced back up again. So its new stable lock point is going to be down there, and it's not at 0 plus because it takes a finite amount of time to get there, but it does get there, and in the process of getting there, it will have generated a control voltage to push it there that amounts to being a steady state phase error. So the feedback loop in the first order loop has to produce an error voltage in order to make it drive to lock again. And that's a really important thing. There has to be an error voltage created to drive it back to lock. What happens in the next iteration of the phase lock loop is we go to a second order loop that has an integrator inside of its loop filter, and then it can keep the static phase error at 0, but in this case, phi, or psi, I mean, is going to have to be non-zero in the first order loop in order to create an error voltage that can push the VCO to keep the frequency error at 0. Is this making sense? And we can move it back, we can move the frequency up and down, but we can already see from looking at this picture that we're kind of bound in terms of how high and how low this can go. Actually, it goes down lower, it goes all the way down here. So it has to be able to pass through 0 if the loop is going to lock. If it cannot, then the loop doesn't lock. It stays out of lock. So this is bullets kind of walking you through it, and I encourage you to look at these because what I've just said may have gotten you more confused. You probably have some sense of what's going on, but so the summary at the end, though, is total lock range is going to be such that omega can go from omega c minus kT up to omega c plus kT. So that gives the total lock range of 2 times kT. And kT has units of radians per second. So this is the total lock range. And you can divide that by 2 pi and get the lock range in hertz then. And then here I'm pointing out that for a given delta of omega or delta f in hertz, you incur some steady state phase error, and that steady state phase error is related to the arc sign of this. This is entirely what one homework problem revolves around. One homework problem is just this alone, this simple equation. So you just need to be able to do an arc sign calculation. Want me to try to find the problem? Or, I mean, it's in the book for sure, but it's one of the problems. So this is an expression that's valid for the first order loop. If the phase error is small, then, in other words, if this phase error psi is small, then the sign of the phase error is approximately the phase error itself. And then we get a real happy situation. We have a linear feedback model. Linear phase lock loop model looks like this. And then we can switch to the S domain, and we can do great things with this using the Laplace transform. And then my venture is to guess is that if you took control systems from Dr. Plett, you were able to just take off and do all kinds of great things, right? So, did some of you take that class last fall? Okay. This was fundamental though, right? So with our phase lock loop, we have the nonlinearity and we cannot escape it because of the fact that we don't necessarily start in lock. So I'm done for the day, but if we can't lock with the first order loop, we end up with, well, here we're locked, so we're staying locked over frequency steps. If we go out of lock, we end up with a situation like this, and we're cycle slipping. When we go to a second order loop, which we'll talk about next time, then it might be too far away to lock initially, but the second order loop with its integrator has this ability to eventually slip cycles in the phase lock loop in the phase plane, and then, bam, it locks up amazingly well. It goes through this nonlinear steps here. And in the process of doing that, this phase plane plot that we're looking at looks like this. It's kind of chaotic, but fundamentally it started at 0, it got totally whacked out, but it eventually was getting closer to the horizontal line here at 0, and then it pulls back in again. This is a nonlinear second order differential equation. Just crazy. I mean, I say crazy because phase lock loops are fun, but they require very delicate hands and some understanding. So I like them a lot, though. I mean, I think in engineering you have to like something that's hard because that's where you can become valuable in problem solving. If you want to flip hamburgers and make French fries, then it's a different thing, right? But each to his own in terms of challenges. So, okay, I'm going to sign off for the day, and we'll be coming back to this stuff next time.